Let's take a look at a couple example problems from Module 14.2 for ME12 Dynamics. So in this example problem here, you can see with our given diagram over here, we have our basic dimensions, 4 feet, 3 feet out there. We have our K value given to us as 2 pounds per foot for our spring constant there. We can see the radius of this wheel down here is given to us as 0.75 from our center here at G. Now in the problem statement, they tell us that the weight of the disc is given to us as 30 pounds, and it has a radius of gyration, K sub G, is equal to 0.6 feet. They also tell us that the spring, again, has that stiffness that we saw in our initial diagram there of 2 pounds per feet, and an unstretched length of this spring here, unstretched, a length of 1 foot here. Now they want us to find the velocity at the instant that G moves 3 feet to the left. The disk is released from rest, so we know it starts with initial velocity equal to 0 in the position shown and rolls without slipping. So there's our assumption right there that there's going to be no slipping involved. So our plan of attack in order to solve a problem like this, we want to do is, since the distance is a parameter and all forces doing work are going to be conservative, we're going to use as our governing equation the conservation of energy. From that, we're going to determine the potential energy and kinetic energy of the system at both positions, and then apply our conservation of energy equation. So with that information given to us in our problem statement and initial diagram, we can now create our setup page. So if we draw a simplified version of our diagram over here, and I have all my given information here. I have the weight is equal to 30 pounds. I have my radius of gyration is 0.6 feet. My spring constant is equal to 2. And my unstretched length of the spring is 1 foot. I need to find my V sub G when it moves 3 feet to the left of this initial start position over here. So now that we've had that opportunity to create our setup page, we can clearly see what they've given us in the problem, our initial diagram, the wording, and what they're asking us to solve for. The next thing we want to do is begin our solution. And as we get into our solution for this problem, one of the first things I want to do is take a look at the spring itself and the position of our disc and see how those are related, how our stretched length, unstretched length of the springs are at the different positions, initial and final, or position 1 and position 2. So to do that, what we do is we can break this initial given diagram down into a really simple right triangle. Because we can see in our given diagram here, we have the length over here of 4 feet, and we have over here in our horizontal direction 3 foot distance there. Now we don't know the length of the spring right here initially given to us, but it's a 3, 4, 5 triangle right here. So we can use Pythagorean's theorem here. A squared plus b squared is equal to c squared. So 3 squared plus 4 squared is going to be equal to 5 squared. So now we know initially when this spring is stretched, the total length of the stretched spring is given to us as 5 feet from that there. Now with this 5 foot distance here, now what we need to ask ourselves is like, okay, that's the total overall length of the stretched spring in position 1. But how much is it stretched past its original length is what we're interested in, is our S value there. So our S value we're going to use here is S is equal to our overall stretch length minus that original stretch length. Now they tell us in the problem statement that the original unstretched length of the spring is given to us as 1 foot. So if we know the whole spring overall length is going to be 5 foot and the initial unstretched length is 1 foot, that means that we are going to be able to go 5 minus 1 is 4. So the stretch distance in position 1 is S1 is equal to 4 feet. So that answers it for position 1, which we've labeled down here. I've drawn out a separate little diagram, position 1, position 2, or initial position and final position there. If we're talking about our final position, position 2 here, now we realize that this wheel is going to roll over without slipping right here and come into this new position over here where it's going to have a length down to the center here of 4. So if this is 4 and the original length was 1, we can subtract the original length out. So the amount that it is stretching here is going to be given to us as 3 feet. And that's simply, again, from taking that 4 foot length minus our original unstretched length of 1 foot. So that tells us now our S sub 2 is equal to 3 feet. So from our little bit of trig here, we see that or our geometry here, we see that we have S1 and S2 values for our spring. And where these are going to become important is when we're starting to solve for our velocity here and looking at our potential energy of the spring. So we're going to want that stretch length, how much that spring is stretched in both position 1 and position 2, and utilize that information into our energy equation. So as we look at our potential energy here, there's one thing that we want to note. So as this disk is rolling and moving over here in this direction here, it's only going to have a horizontal component and no vertical component. It's going to stay in contact with the ground. So what that means is that there's going to be no change in our gravitational potential energy since it's moving purely horizontally and not vertically at all. So that means our only component for our potential energy is going to be from the spring and not from our gravitational potential energy, because that's going to be 0 there. So the next thing we want to do is break this down into our two different positions. Position 1 initial, position 2 final. So the diagram here shows it in its initial position here, position 1. We have our governing equation here. Potential energy for spring is equal to 1/2 Ks squared. So for this case here, V1 is equal to 1/2 Ks1 squared. We write that out there, and this is why we needed that S1 from the calculation on our previous slide there. And we have a value given to us of our spring constant in the problem statement. So V1 is equal to 1/2 times our K value of 2 times our S1 that we found to be 4 squared. We do out our math there, and we have our potential energy here of 16 joules. Now we can do the same thing over here now for our second position here. So our second position here says V2 is equal to 1/2 Ks2 squared from our governing equation potential energy for spring. So V2 is equal to, when we plug in a K value of 2, our S2 that we calculated to be 3, do out our math there, and our V2 is equal to 9 joules. So now that we have our potential energy for positions 1 and 2 of our spring, the next thing we want to do is take a look at our kinetic energy. So with our kinetic energy, remember our governing equation right here. For our particular problem, we have 1/2 mv squared for our kinetic energy equation right there. And then for the kinetic energy, for our particular rolling disk problem here, we 1/2 I sub g, where I sub g is our moment of inertia, times our omega-2 squared right there. So one thing to notice is that if this disk is released from rest, so it starts with no velocity there, then our initial velocity is going to be 0. So our Vg1 is equal to 0, which means that our omega-1 is also equal to 0. So then what we're really concerned about is just our position 2 over here. So for our position 2, we have our omega-2 as our angular velocity, and our V2, or our V sub G2, is equal to our velocity at the center of mass of our disk there. So that's where this kinetic energy equation comes into play. So again, we have the part from 1/2 mv squared, and then we have the one for our rolling disk over here of 1/2 I sub g for our moment of inertia times our omega-2 squared. Now, what we want to continue with this is, what is our relationship for I sub g for our disk here based upon our K sub g, or our radius of gyration? So recall this governing equation here, that our I sub g is equal to 1/2 m times our K sub g squared, where we're given our K sub g, our radius of gyration, as 0.6 feet, and we're given our mass as 30 pounds. So those are things that we can now plug in for our I sub g. We can take this relationship here, plug it in right there for our I sub g, and for our mass, we can plug our mass in right here, and we can also take and plug our mass in right here. And again, for this is our kinetic energy equation for position 2, because we don't have a kinetic energy at position 1, because our initial velocity is 0, because it starts from rest. So we start plugging into that kinetic energy equation there, say 1/2 m, our mass right here. So we take our weight in pounds of 30 pounds divided by acceleration due to gravity of 32.2 feet per second squared, times, this is what we're looking for here, our velocity, our V sub G2, quantity squared, plus 1/2 our mass here, which is still the weight divided by acceleration due to gravity again, times our K sub G, our radius of gyration. Again, I've included these all right over here to the side, just so we know what to plug in. This is 0.6 given to us here by the problem statement. Quantity squared times our omega-2 squared. So at this point here, we can simplify this down and do some math, but what we notice here is we have one equation, but we have two unknowns. We don't know our omega-2, and we don't know what we're looking for here, our velocity at the center of mass of our rolling disk. So we do have the assumption that we made here that the disk is going to roll without slipping. So if our disk rolls without slipping, we can use this simple relationship here, that V is equal to omega r, which we've seen through many courses and the beginning of this course. So with V is equal to omega r, we do have a value given to us, which is r is just the radius of that disk there. So that's 0.75 feet. We can plug that right in there. So we now have a relationship between our two unknowns. We didn't know, our two unknowns were V and omega. So now we have a relationship between V and omega there. So V sub G2 is equal to 0.75 times omega-2. So with this information now, we can go back to our governing equation for kinetic energy, our T2 equation here, and plug in now, and there's two different ways that we could do this. We could have plugged in and eliminated omega 2, or we could plug in and eliminated our V sub g. I chose to plug it in and get our omega 2 first here. So when we do that here with our omega 2 first here, we end up with one equation and one unknown, and we can see all of this can be simplified down, so we just have our T2 equation dependent upon our omega 2, our unknown there. So we now have omega, or T2 is equal to 0.43 times our omega 2 squared. So with this here, again, recall what we really want. We can go back to our setup page, our problem statement. We need the velocity of that rolling disk. So we need our V sub g2. So that's what we're really interested in. So where do we go from here with our now relationship for our kinetic energy, T2, with respect to our omega term? Well, now we're going to go back to a new governing equation here using our conservation of energy. So recall for our conservation of energy, we have two positions here, initial and final, 1 and 2. So for conservation of energy, our governing equation here is T1 plus V1 for position 1 is equal to T2 plus V2, our position 2 there. So we have our kinetic and potential energy at position 1, kinetic and potential energy at position 2, where I like to come over here, write down everything I know right underneath my governing equation, so it's a plug and chug from that point forward. I know that my initial kinetic energy, my T1 kinetic energy, my position 1 is equal to 0. I've already solved for my potential energy for both position 1 and 2. So for position 1, it's 16 joules. Position 2, it's 9 joules here. And my T2, I now have a relationship for that's dependent upon my omega 2 there. So I can take all these, put my 0 in for T1, put in my 16 for my V1, put in this expression here, T2, right there for T2 in the kinetic conservation of energy equation, and my V2, I have a numeric value I can plug in there. And when I do that, I end up with this relationship here where I have 0 plus 16 is equal to 0.43 times my omega 2 squared plus 9. So the only unknown in this is my omega 2. I can solve this, rearrange, and simplify, and get the fact that my omega 2 is now 4.04 radians per second. But that's not exactly what they asked us for. They didn't ask us for our angular velocity. We want our V sub g for the velocity of the center of mass of our rolling disk here. So we need to now go back to our relationship, V is equal to omega r, and plug in there to get our V. So we do that there. We go back. We remember that this is a no-slip assumption we're making given the problem statement. So we have our governing equation of V equals omega r. This is our V sub g2 for our case here, our omega term right there. We have there in our r term right there. So we can plug in those values. V sub g, when we do this out and simplify, is equal to 3.03 feet per second.